In the universe, the most distant objects are also the oldest. When we look at the Andromeda galaxy, we see him to 0.50 million years ago. The sunlight reflects the light of Jupiter. It takes 30 minutes to reach us. And even closer objects, we don't see them as they are now. The earliest light ever detected by scientists, when the universe was born, hundreds of thousands of years after birth, produced by the Master. This early light helped us discover the universe. Big Bang. But what caused the Big Bang? The universe preceded an event, maybe dormant. He may have collided with another universe, or he could be a cosmic explosion and part of the eternal cycle of bouncing. Why was the early universe invisible? How energy defines time? Why is 97% of the observable universe forever? It's beyond our reach. Will this all lead to another Big Bang? To understand the origin of the universe, scientists use a telescope to observe the farthest reaches of the universe. When these telescopes detect light from distant galaxies, they are actually catching light that began billions of years ago. Because light needs time to travel through space, and since the universe began to expand, the journey of that light has also been lengthened. We can see diversity depending on the universe, the distance that light can travel since it began to expand. The original photon cannot move freely. They are constantly being scattered by free electrons, made the early universe opaque. About 380,000 years after the Big Bang, these primordial photons are released, keep moving in their current direction. During their long journey, the wavelength of this light is stretched very long, moving from the visible spectrum to the microwave range. Researchers are detecting this was discovered during the microwave background radiation. During this time, everything beyond our observation range. So, scientists rely on predictions to understand how early the universe, what might happen during the period. As time goes by, the total damage of the universe keeps increasing. Simply put, it expands and becomes less usable. Stars explode into supernova. The black hole will slowly evaporate. Hot things cool. Injuries determine how we define time. Usually, what we call the future is just a wound, high or energy, more scattered state. The state of lower injury, let's call it the state of the past. So the more we cut back, the quotient is lower. We don't know why this is happening, but this is something about the universe. Fake before the Big Bang, say the things around. Some physicists have proposed the universe was dormant before the Big Bang. According to this view, he used to stay tight and still, and then at a certain moment, change caused by a certain trigger, the universe before the Big Bang, considered to be a venta. It just looks stable on the surface, but it's actually a ticking time bomb. In the scientific community, this state is also known as a false vacuum. To understand this concept, you can imagine a valley among the mountains. People in the valley may think this is the most stable, fixed place. However, beyond these mountains, it's a cliff that leads directly to the ocean. It's the ultimate state of minimal energy. The same young universe may exist in a vacuum, until some kind of catalyst sets in. He transitioned to a truly stable state. Now, what set the universe in motion? In the world of quantum mechanics, there's a lot of uncertainty about how these particles behave. If the universe before the Big Bang was affected to the domination of quantum theory, then anything can happen. Imagine an underground river flowing below a valley. It slowly took away the little pebbles into the sea. This continuous flow gradually weakened the foundation of the valley until a tipping point is reached and the valley collapses. And this is what we think. How did the universe expand rapidly through the Big Bang? For a long time, all matter and energy are contained within a point of view widely accepted. Modern physics today holds that there is no such starting point. Instead, the phenomena that led to the origin of our universe is the expansion of the universe. He began in a cold and empty space. It's one half the size of a proton, but he was so full of energy. Internal pressure generates a platoon. Repulsive attractive force. This force triggered an amazing expansion. The universe in a short period of time, 80 times the size. Then it caused a fiery Big Bang. Imagine a bomb about to go off. First, the explosives start to decompose, generates hot gas, and releases energy. As the gas accumulates and disperses, they put pressure on the bomb's inevitable release. Only after this, the explosion happened, also used to drive the expansion of the universe. All the energy of the expansion is released into space. It heats it up and produces different particles. At this moment, the universe has expanded to hundreds of billions of times its original size. Once concentrated and intense energy, now scattered over great distances. However, the quotient can also be interpreted as everything from an unlikely state of order transform into a more trends towards possible chaos. But the seemingly ordered universe we observe today is teeming with all galaxy clusters and galaxy systems. How early, the mixture of extremely hot particles is even more chaotic. Imagine the Big Bang as a party microphone. When you pull the rope, he burst into a colorful confetti. We expect confetti spread chaos in all directions, form a random color fragment. Instead, we see confetti. They organize themselves into perfect numbers and geometry, object circle, square triangle, and these represent the subuansi, particle circles and molecules. And not only that, no matter which direction the researcher takes, universe seems to be uniform in all directions. They are present throughout the universe. The measured temperature is 2.7 K. Left and right, this shouldn't have happened. Here's why. Although the age of the universe is estimated at 13.80 billion years, but the range of observation is much larger. Today we can observe the distance from the Earth, 46 billion light years away. Therefore, the diameter of the observable horizon is 92 billion light years. And that's because space itself is expanding faster than light. But information-carrying particles have limited velocities. So to points in space more than 14 billion years apart, how do they have the same average temperature? This is called the horizon problem. And the flatness is a mystery. Einstein's theory of relativity is solid. Large objects bend space-time, affects the movement of matter within it. In some areas, galaxies and black holes are irregular in the fabric of space-time, but on a much larger scale, these irregularities are evenly distributed. This results in a smoother structure. This overall uniformity suggests that the universe videos on large scales. So why does this happen? There is a view that the expansion of the universe will never stop completely. On the contrary, there is a highly damaged parent universe that continues to expand, only stop in certain areas. No matter when he stops, a new low-damage universe will form him. They are isolated from each other. Maybe these sub-universes has been created in an endless sequence. The Big Bang fits this theory very well, but it doesn't mark the beginning of the entire universe. Just a small part of it is by more, caused by quantum fluctuations that occur on large scales. Although there is still life as a whole, but over time, the number of lives will increase. Each universe runs out of energy. It cools down and stops. But at the same time, more universes are being created. Because every possible universe would exist, so there will be life. And with the creation of new sub-universes, life will become more. If the concept of eternal expansion is true, then there must be an infinite number of universes. Every universe, each has its own unique nature. So there is a universe like ours. It was inevitable, seems tailor-made for life. Stars produce key elements. Everything works in harmony. Or the explanation might be simpler. We don't need multiple universes. There are different variants of the inflation theory. The model proposed by Davin Goss holds that the expansion of the universe, it's not constant in the early stages. The universe is small. Those lines are in regions of space that are very far apart. It was close, enough to exchange materials. And then, space has increased 80 times in a short period of time. Then the expansion slows down, continue in a more stable manner. Even now, the universe is also expanding rapidly. If scientists had a computer that could travel at the speed of light, moving detector, they sent him today to explore the universe. It only covers about a third of the observable horizon. That's about 3% of the volume of the universe. This means that 97% of the visible universe has exceeded out of our reach. Therefore, we will always, far from certain, is the universe as a whole consistent? The universe we observe, just a speck on the canvas of the larger universe. In our little corner, things may appear uniform, like the flatness of space and the overall temperature balance, but like a broader perspective, reveals the same zonation of the Earth's surface. A broader view of the universe may reveal that our limited perspective, unnoticed changes. Before the expansion, the universe may have large temperature differences. When the universe was expanding rapidly, some places are pulled too far to see, may hide those changes. If the Earth were sufficient, small enough to fit in your hand, then he will feel like a perfect ball. You can't even see Mount Everest. Many scientists believe that the idea of perpetual expansion is depressing. If each individual universe have different laws of physics, so why study particles in our universe? What about behavior and laws? The more popular hypothesis is a cyclic universe, a universe that appears and disappears repeatedly, rather than endless expansion. This model of the universe will go through different stages of expansion and contraction. Every cycle is a big bang, a huge burst of energy, launching a new era of cosmic evolution. As the universe expanded and matured, galaxies appeared, stars and complex structures. But as time goes by, a mysterious force, dark energy, has captured the attention of scientists. He came to dominate, pushing the universe to expand at an even faster rate. By the relentless push of energy, finally overwhelmed gravity, causing the great collapse. Everything collapses back to the starting point. But that's not the end. This is just the beginning of the next cycle. Another big bang. Reignite the rhythm of the universe. Repeat this process endlessly. Some physicists believe that the significant contraction of the universe may not be a major collapse. Necessary conditions for occurrence. When the universe as a whole shrinks, the observable horizon shrinks faster until it becomes tiny. When hidden in, when the boundaries of the world beyond our field of vision approach us, we won't be able to see most of the universe. So let's start with this. Distant galaxies will disappear from our sight. And then the stars in our own galaxy, and then closer objects. Mars and the Moon will also be invisible. Gradually, people can't see what's in the room. In the end, even man himself will disappear. This terrifying process will continue until a single particle is isolated, cut all contact with its surroundings. Everything becomes static. Everything in time and space is frozen. Once active structures and entities become static. That goes on until the cosmic horizon begins to expand again. If the universe experiences endless creation, the cycle of creation and destruction, we will eventually experience another collapse. Will this happen? Depends on the overall regionality and density of our universe. The fabric of space-time contains vast amounts of energy and matter. This collective attractive force could make the universe right. Curvature like the surface of a sphere. This zone rate has a unique quality. It folds the canvas, would effectively slow the expansion of the universe by itself. This could go further, completely reverse the expansion of space. Everything will crumble in the Great Collapse, once scattered across the vast expanse of the universe. Mistakes end up clustered in a small space. But if the total density of matter is sparse, then spacetime may have a complex rate. Shape is similar to safety in such a universe, despite the attractive forces. But he lacks resistance to the expansion triggered by dark energy. The power in this situation. All matter in the universe will continue to increase. Added velocity diffusion. Make the universe infinitely larger. The expanding nature of the universe, for another fascinating hypothesis, laid the foundation. This hypothesis involves extra dimensions and based on explicit theory. It's called brain cosmology. Xiang. All existence is a vast cosmic book. Each page of the book exists in a way that is larger than the book itself. Lower is red weight. Scientists call these planes the brain. The idea is that they represent different universes. Every universe, according to a set of unique laws of physics, do their own thing. These brains can move and collide. When they collide with each other, they generate a lot of heat and energy, cause a big bang. Our current understanding tells us that. As time goes by, the universe got bigger and colder. This means that long ago the universe was hotter, denser, although we may not know. But 13.80 billion years ago, the universe was born. But what happened after the Big Bang? Planck time and Planck length, to basic units in physics. In order to understand these concepts, imagine a photon traveling at its maximum possible speed through space, speed of light. The photon is traveling some distance. The distance is so short, so much so that he is measurable in the universe. Minimum length of quantity. Planck time is this speedy photon crossing, called Planck, the minimum length of the exact time required to divide the distance. These two units both represent the boundaries of our current understanding of physics. Boundary measurement. After the Big Bang, 100 trillion, 100 billion, fraction of a second, it's called the Planck era, is now the earliest period that modern physics has been able to explore. At that time, the size of the whole space is a Planck length, trillions of times smaller than a photon. The temperature of the dust here is absolutely hot. He is absolute zero. Instead, in a supernova, 100 billion open ears inside the core of a child star. Quantity and comparison with Planck temperature. Contact. Temperature reflects the motion of particles, energy and vibration intensity. Basically, the hotter he is, the faster he moves. Physicists believe this is unpredictable. The age of quantum bubbles. Everything vibrates and changes randomly, generating microscopic black holes and impulses. Once these holes are formed, they will disappear. With the huge explosion of the Big Bang, the universe is filled with a unique, all-encompassing power. This is gravity, the fusion of the weak and strong sum forces of the electromagnetic force. The period of great unity continued with a brief window of surprise, until the -36 seconds after the Big Bang, when the universe was still a boiling universe. The energy furnace is at this moment. Scientists believe that the fundamental forces of nature began to separate from each other. The first is attractive force. He appears as a unique corpse, shaping the future dynamics of the universe. In this era, energy levels have reached an astounding 1028. Electronic Ford. To illustrate this point, the energy of the universe in pulsation. is large, the Hadron Collider can achieve 1 trillion times the energy. As the universe gradually cooled, strength and force finally break free. About the -12 seconds after the Big Bang, the electromagnetic force and the weak force are separated from each other, and soon after, Higgs field appeared. That's what gives rise to the Higgs sieve. This is a method that gives other elementary particles, such as the example of quark mass. At this point, the temperature of the universe is about the 14th power Kelvin. As particles interact with the Higgs field, they got mass. This process is known as the Higgs mechanism. They basically shape the building blocks of the future of matter. At some point, something happened to the early universe. Crucial process. Become a seed generator. Scientists don't know the exact time of occurrence, but this hypothetical event, it happens at very high temperatures. The random motion of particles occurs at relativistic velocities. When particles and antiparticles collide, they drown each other, but matter prevailed. Exceeds antimatter, and that asymmetry causes a little bit more matter. About every 1 billion antimatter particles, one more proton. This seemingly insignificant difference, for a universe dominated by matter, fixed basis, shaped the trajectory of the universe as we know it today. The basic conditions seem to be in balance. About a microsecond after the Big Bang, the temperature dropped to the power of 10 to the 10th. Open ears allow quarks to form protons and neutrons. Towards the end of this period, the universe is about a second old. 3 minutes after the Big Bang, the temperature plummeted below 1 billion Kelvin. This allows for synthesis. In this brief period of time, generated a large number of hydrogen nuclei, such as hydrogen and harmful protons and neutrons combined to form these nuclei, generating heavier elements for future stellar processes. Prime planet. The journey of stars and stars paved the way. About 380,000 years after the Big Bang, the temperature dropped to 3000 Kelvin. The first molecule is made of hydrogen and C. This marks the transition from pure atomic matter to molecular complexity. The combination of C and hydrogen launched a new era of chemistry for the emergence of more complex molecular structures. Ready? Now the electrons are bound to the river. Photons can travel freely through the universe. No obstacles. The appearance of neutral hydrogen and harmful atoms, causing the first light to penetrate the universe, illuminate his history. The universe becomes transparent. Future human civilization. We go all the way back to light. Over the next billion years, as the universe evolves, dark matter is a matter that does not emit light, shows its attractive force. Physicists believe that dark matter weighs 6 times more than ordinary matter. About 500 to 600 million years ago, dark energy begins to dominate the expansion of the universe. So far, the nature of these forces remains a mystery, waiting to be revealed. Understanding the past will help us see the future. But what fate awaits our universe? These cosmic mysteries, it invites us to explore the unknown.